So, good evening, everybody. My name is Francesco Casella. I'm here to briefly present Open Modelica. I guess everybody will be quite tired at the moment, so I'll try to hopefully not to make it too boring. I have to ask the audience a question before we start. How many of you are actually using Open Modelica already? So many, but not all. Because, I mean, to me, it was a bit difficult to set up this presentation because it's one thing if you talk to someone that wants to know more, and it's a different thing if you want to talk to someone who's been using that for a while. So I tried to strike a balance. I hope I'm boring all of you equally. If I manage to do that, I would have done a good job. All right, so this is quickly the outline of what I'm talking about this evening. What is Open Modelica? That's for the newbies. Some recent improvements, ongoing developments, and most importantly, a few words about the open source Modelica consortium that supports the development of the software. So what is Open Modelica? This is taken straight from the website. Open source, Modelica-based modeling environment, both industrial and academic usage, and supporting, as we said, by the OSMC. This is the whole story in a nutshell. Let me briefly spend a few minutes about some key components of this environment. So it's many pieces of software that work together. The core of the whole thing is OMC, the Open Modelica compiler. I would claim this is, this has been developed for more than 20 years now. And I would claim that it's now really a full-fledged Modelica compiler. It supports there are a couple holes, all Modelica 3.6 advanced features, replace and redeclare, conditional components, over-constrained, connector stream, homotopy, synchronous dynamics, dynamic select, whatever. So long gone are the days where Open Modelica was doing a little bit here and there. It's available on 64 Windows and Linux distros, already compiled. You just download it and install it. You can get it on macOS via Docker. I understand there's plenty of people that instead of playing Sudoku, they like compiling Open Modelica from sources on whatever crazy hardware and operating systems. Everybody is entitled to his own amusement. It's surprisingly lots of people doing that. It can run as a command line, contrary to Daimola. This has been since the very, very beginning. Or as a DLL in the background. For example, this is how you can develop a GUI. You can leverage on OMC to understand what Modelica model compiles and just interrogate it. I'll go back to this in a minute. It used GCC in the past, but now it uses C-Lang, which is much faster at compiling. And it can exploit multi-core CPUs, both for code generation, compilation, but also simulation. I missed to mention that. Yeah, I could go on for hours. I'm trying to keep it short. The compiler does lots of symbolic manipulation and numerics on the Modelica code. So things which are well-known, alias elimination, index reduction. It can handle under constraint or over constrained initialization problems pretty well since a few years. Dynamic state selection is supported, tearing. We're also experimenting user-guided tearing with annotations that specify what are the most favorable tearing variables based on the user understanding. Clock semantics, and also automatic parallelization of generated code. OMC uses state-of-the-art numerics. It uses both dense and sparse solvers. Sparse solvers were introduced 10 years ago, so I think we pioneered that. We have homotopy support. OD solvers, Dussel is still king, but we also get IDA, which is actually supposed to be a bit better, CVOD, and most recently GBOD, which is a new generic Runge-Kutta solver, mainly written by Bernard Bachmann, which is starting to work quite well. We also provide the DAE mode integration. Instead of turning the DAEs into causalized ODEs, we can keep them as DAEs and solve them with IDA and with a sparse solver. Most importantly, this is a part that I'm very proud of. We try to provide advanced debugging support. I'll show you a small example in a minute. We have a support for visualization of solved equations in the GUI, support for algorithmic debugging of Modelica functions, and recent additions, diagnostics of Newton solver failures. There will be a presentation on Wednesday morning if you're interested. And last but not least, SVD analysis of singular and badly scaled Jacobians. This is still a bit experimental, so next conference I hope I will be able to actually show some nice demo about that. So on top of OMC sits the GUI OMEdit, started with like something quite similar to Daimola, obviously. Yeah, I'm not doing any live demo because that's too dangerous. So I'm just showing you some. It works quite well, but you know, Murphy's Law. So I'm just showing you some static snapshots. So of course you have all the usual things, documentation, library browser, graphical view, textual view. You can load the results and analyze them and zoom them. We have some quite nice features with automatic selection of units with the right prefixes. So if it's millimeters, you see millimeters already, but I mean, nothing fancy. There's some decent 3D multi-body animation included. This is the robot example of the Modelica standard library. It doesn't move because this is just a PDF, but I can tell you, I mean, you can download it and test it. It actually works quite well. And also dynamic select. This is the par grids library that allows you to see per unit voltages, active and reactive power flows, also in an animation if you need superimposed on the system diagram. This is an output from the equation-based debugger. Now, this is a problem. The equation-based debugger needs an 8K screen. The larger, the better. So I'm not sure if you can read, but what you see here, this is the sequence of computations which is carried out on the generated code. That's more or less what you see in the dsmodel.mof file of Daimola, for those of you who are familiar with it. So here you see the last three initial equations, which actually turn out to be asserts. Here the regular equations start, which are the ones that are solved at every time step. So you see lots of them were solved symbolically as assignments. But then here you see a nonlinear Thorne system with 5 unknowns and 1 iteration variable. And here you see 4 Thorne equations and 1 residual equation. Now, if I'm selecting this equation here, I can actually in this window see how this equation was transformed in this actual form from the original source code. In this case, it was just a stupid step. It was solved for whatever, R1.v, but there could be many steps of symbolic manipulations, of substitution, or whatever. And eventually, this links me to the original source code here. I think this is quite nice. Unfortunately, this is still completely static information, so we don't have any information during runtime. If something fails, we would like to see the values of all these variables and these kind of things. We're working on that. And also, if you write non-trivial Modelica functions, you can also debug functions. This is a regular function debugger. It's just integrated in Modelica environment. This also works quite well. You have all the standard features, breakpoints. You see all the local variables. You get the function, how do you call that? The stack trace and whatever. Yeah, I need to speed up a bit. FMI support, alas, is still mostly focused on FMI 2.0, but we're working on it. So we have model exchange and co-simulation export, both with explicit and implicit solvers. This can be interesting. You can get FMUs with full source code that can be built using CMake. And again, here I know people who are making crazy things trying to compile these FMUs wherever. And most importantly, the generated FMU is free of any license. You can run it wherever you want. We are working on FMI 3.0. I hope at the next conference I will be able to show you something more interesting. And last but not least, we have a part of the environment, which is a software called OM Simulator. It's a simulation tool compliant with FMI and SSP, so it can simulate aggregated FMUs. Both co-simulation and model exchange with CVOD, and it has a GUI which is integrated into OM8. I would briefly mention this. This may be interesting for some applications. Open Modelica defines an API, so it functions to all the actions of the compiler, loading a file, building the code, simulating a model, querying a class, what's the name of your components, what's your ancestors, changing parameters, all these kind of things. So there's this generic API. This can be invoked by writing scripts that you can run at runtime, possibly from the command line. Or it could be invoked dynamically through a DLL. For example, the GUI or OM8 actually talks all the time through this API to the compiler to get details about the models that have been loaded. And then we have two environments, OM Python, this is more developed, and OM MATLAB. We also have an OM Julia, which is still, it's not up to date, so I did not really mention it here. So basically, from these tools, you get access to this API within a Python environment or within a MATLAB environment, and you can automate your stuff as you please. Package management. Open Modelica includes a package manager for open source libraries. We selected more than 160 open source Modelica libraries available online. Some of them are old or experimental or whatever, but there are 80 which we believe are quite interesting and good, and we actually tested them on a nightly basis to make sure that we are not breaking up everything. By the way, the results of this testing are available online, so everything, there's no secrets. What is nice is that these libraries can be managed from within the GUI. You can say, give me a list of all the libraries with full support, or maybe just with experimental support. You get a list, you can install either the last version or a specific version. And what is nice is that the package manager automatically figures out the dependencies. So I want a library XYZ, you say install it, and it will install the dependency automatically, and then you just say, okay, now open it, and you're off to go. As long as these libraries have been properly released on GitHub, this is also the updates, we get them automatically. So that's more or less part of the story. There would be more like optimal control and other stuff, but I still have 7 minutes, right? So I have to speed up even more. Few words about recent developments the last couple of years. On the compiler, I mentioned GBOD already. We improved significantly the code generation speed by optimization of the code. I also mentioned this diagnostic method for failures of nonlinear systems. This is new. And since Doug mentioned that, eliminating part of the systems that do not affect its outputs, we also got that. It's under a flag. OM8 has been improved a lot. There's hundreds of bug fixes. So if you're still using 1.23.1, please always update to the latest version. It's worth it. There's 2 of them coming out, one in spring and one in late autumn. We improved the robustness, the speed of response. Now we have a decent handling of parameter arrays, which was a bit weak. Sometimes it was even generated illegal Modelica code. That was not good. Improving copy and paste, so it's now really usable. We also added some sorely missing features like editing of top-level parameters, hierarchical editing of parameters in submodels, replaceable classes support with drop-down menus, all these kind of things. Duplicate, reload, whatever. Also, rounding, this was really bad that we got something like, I have a parameter which is 500, so we got 499.99999. That was really bad. That has been fixed. I wrote the code for that. And last but not least, we have an experimental implementation of base Modelica, flat model output. I cannot tell you about base Modelica now because of lack of time, but in a nutshell, the idea is you can use Open Modelica to get a complex object-oriented structured model into a flat Modelica model using this language, which is still not standardized. We're working on it with the Modelica Association, which is basically Modelica without the object orientation. So it's much easier to read the equations from there than to write a full-fledged Modelica compiler. This can be used for multiple applications. FMI export has been improved in terms of bug fixes. As I mentioned, we have this CMake-based source code FMI export that can be useful. And we also improved the co-simulation with CVOD, which was really a bit shaky. Couple of words on, there's lots of things going on now. You can also have a look at GitHub and see the tickets. There's lots of stuff. I would focus on a few things which I believe are interesting. The most important to me is array preserving code generation. Several years ago, we already made a completely new front end that does the flattening without unrolling the arrays. That is kept as the last stage, so we can keep them together. And the objective, and now we are continuing with the rest of the tool chain. The objective is to reach at least 1 order of magnitude faster code generation performance compared to the Open Modelica that you see now. And also have much smaller memory footprint for simulation executables because you avoid repeated code. Runtime resizable arrays, which is a hot topic within open scaling. And this is made possible by the new backend that does all the symbolic manipulation, trying to preserve arrays as much as it can. This is still experimental at the moment. We're working on it. I hope that there will be some interesting use cases working in 2026, most notably models of power grids models. We have a cooperation with the French transmission system operator, which is already using Open Modelica in operation, but in a slightly tweaky way, and because for large models, they basically compile individual components and then they assemble the C code manually with their own workflow. The idea is that starting next year, we should be able to compile the entire French network in like 2 or 3 minutes and then just run the simulation. Also, large 3D thermal models with large 3-dimensional arrays are for sure interesting for some applications. And then hopefully this should become the default backend 27, 2028, we'll see. We're experimenting on advanced numerical methods for efficient simulation of large systems, multi-rate and mixed implicit-explicit multi-rate integration with the idea that everything is automatic. You just click on a button and get faster simulation. And improving the debugging support basically by integrating what we currently have into the graphical equation-based debugger that I showed you. And last but not least, I mentioned FMI 3.0. 3 minutes to go. Oof. So let's. I will probably have to skip something. 2 words about licensing. Open Modelica is open source. The code is owned by the nonprofit Open Source Modelica Consortium. Contributors assign a CLA. We have a dual license software. You can use it as GPL, basically. Or if you join the consortium, you can also use it to modify the code and link it, compile it with your own proprietary software without the GPL provisions. Binaries can be executed freely, as with all GPL software, and also the generated code can be generated freely. Why is it good to have open source? Well, the easiest answer is you don't pay a license. That's good. Also, your customers or associates don't pay a license if you want to redistribute your model. That's also potentially interesting. You can run simulations massively on the cloud without any problem with licensing. That is also interesting. This is an important point, for example, for RTE, the credibility of your simulations. There's no secrets or no confidential IP on numerical and symbolic methods. You know exactly, at least in principle, how your Modelica models are handled. Everything can be inspected in terms of what the code does and improved, possibly. I'm not saying excusatio non petita. I'm not saying that commercial Modelica tools are bad. I'm just trying to make you understand what is the difference. And last but not least, you can contribute directly yourself with feature of your interest. For example, I just mentioned this thing here. EDF has a lot of interest in requirement modeling. They define this common requirement modeling language, or maybe they took it from somewhere else, and basically they defined an extension of Modelica to handle requirement modeling and verification. And thanks to some collaboration with the Open Source Modelica Consortium, integrated this functionality into a Modelica tool, which is OMC. This can also happen through contracts that are signed between people and the consortium. So I have 1 minute to talk about the open source Modelica consortium. It's about 50 members, half companies and half universities. These are the benefits of joining. These are the legal ones. There are some things that you can legally only do if you join the consortium. Basically, skip the GPL thing, or possibly have a specially compiled binary version which supports encryption. But then there are other important points which go beyond that. Basically, you become active part of a community and you support the long-term success and thriving of the tool. And yeah, that's it. Thank you for your kind attention.